this little activity, and it said on each graph above, draw the tangent lines at the points shown. Circle the best answer for the concave up graph. Are the slopes increasing or decreasing? Well, if you were going to try to give a numerical value to this slope, would you agree it's like -10 or something really steep, right? And then maybe -9 and -8, I don't know, right? But it seems to be doing what? Okay, and so less negative and more positive than we are increasing, right? Our slopes are definitely increasing on the concave up graph. I don't know, won't we? So for the concave down graph, what do the slopes appear to be doing? Decreasing. They start out as steep, positive slopes, they get less steep, and then they turn to negative slopes that are still decreasing. So, you're telling me that if the slope is increasing, then I have a concave up graph. The slope of the slope, right? Because tangent line is already. So, what derivative are we going to be looking at today, do you think? Second derivative. So, definition of concavity. Now you know concavity as science definition, right? KZ, right? If f of x is differentiable from a to b, f of x is considered concave up if the first derivative is increasing, or, which I think is on another slide, but we'll go ahead and say it here. If the first derivative is increasing, or, what would that mean? The first derivative is increasing, is positive. The original function would be concave up if either two of those conditions are met. If f prime is increasing, or the second derivative is greater than 0. The function, the original function would be concave down if the first derivative is decreasing, or the second derivative is less than 0. I stole this activity from something else that's about to lead you to that conclusion, but we'll talk about it. You don't have to write this down, but why does that make sense to create the concavity that you're used to thinking about? Why would an increasing slope create a concave up function? Or why would a decreasing slope create a concave down function? Any thoughts on that? Why would an increasing slope, so a slope that gets steeper, so you have a slope and it gets steeper, why would that create a concave up? And why would a slope that gets less steep create a concave down? We're still on spring break. Yeah, for example, like an exponential function, right? On an exponential, your slope is always increasing. So it creates that concave up shape, right? If your slope is increasing. If your slope is decreasing, like a square root function or something, creates a concave down shape. When we say that f prime is increasing, we mean that the slope of f prime is positive. However, the slope of f prime is the slope of f of x. So we were kind of talking about it. Thus, we can reword the definition of concavity in terms of the second derivative, which is, we're about to write that or part down as its very own definition. If f of x is concave up, then f double prime is positive, not increasing, positive. F prime would be increasing. And if f of x is concave down, f prime would, double prime would be negative. Second definition of concavity. So if we are asked to find if a function is concave up or concave down, we're going to find the second derivative and do a sign chart. See if we're positive or negative. Positive will be concave up, negative it will be concave down. So we can learn a lot about a function using derivatives. We can learn the increasing and decreasing maxes and mins from the first derivative, and from the second derivative we can learn concavity and get the shape of the graph. So you're going to do a lot with curve sketching with the first and second derivative. This is just a visual of what we just talked about and another definition. So we have a concave down graph and then a concave up graph. The points where your graph changes concavity is called a point of inflection. Points of inflection occur when the second derivative is 0 and changes signs. Star this in your notes. My AP Calculus kids miss this all the time. Despite how many times I say it, I'm going to try to say it a few extra times this time. Maybe it'll work. Points of inflection are not places where the second derivative equals 0. That's not enough. Yes, it has something to do with that. Points of inflection are what maxes and mins are to the first derivative. Not only does the second derivative have to equal 0 or be undefined, but it also has to change signs. Now, it doesn't matter how it changes signs. It can change from positive to negative or negative to positive. But the second derivative has to change signs. Because a point of inflection happens at a change in concavity. We could have a fake, just like we talked about with maxes and mins, a place where the second derivative equals 0, but it doesn't have a sign change, and that would not be a point of inflection. So points of inflection have to meet two criteria. The derivative has to either be 0 or undefined, and there has to be a sign change on the second derivative. And those points, graphically, are the place where the graph changes concavity. It goes from being concave down to concave up. So, we're not going to do any algebra yet. Just visually speaking, I want to look at where would points of inflection be on the graph. So, visually, where would we have our first change in concavity? Somewhere in here. Concave up, and then somewhere in here changing from concave down. I don't know exactly where. We'll have to find out. We'll do that algebra momentarily. And then somewhere in here. So let's find where the somewheres are. It does give us a function. It's x to the 4th minus 12x squared plus 8. If I want to find points of inflection and concavity thoughts, where do I go with my function? Second derivative, which means I have to find the first derivative first. How do you know this is right now I'm just visualizing. I don't know exactly where it is, but do you see how this appears to be concave up? And how this appears to be concave down? Other than that, I don't know numerically where they are yet. I just have a visual that there's something. We're about to find out for sure. I need to know when the second derivative is 0 or undefined. The math part of this, the algebra, should be still almost identical to what you did last week with the first derivative. But now we're doing it with the second derivative. We're going to find the zeros, do a sign chart, all the fun stuff that we did last week. So I'm going to factor out a 12. And I get plus or minus the square root of 2. Everyone see how I got that? I'm going to make a sign chart. Now, I told you last week to label your sign chart. You're probably like, well, why would I do that? Here's why. I'm going to label this sign chart as a y double prime sign chart, so I know what it's telling me. You will have problems where you do both sign charts, so you'll want to know which one's which and what it can tell you from that. So if I plug in something less than -2 into the second derivative, negative radical 2 into the second derivative, -4, something like that. What would I get? Positive number. If I plug in something between negative radical 2 and radical 2, 0 is a good candidate for that. I would get a negative number. And something after radical 2, I would get a 1. Now, you don't always have to draw this, but we did it for the first derivative sign chart, and I want to do this for the second derivative sign chart to let you know what the sign chart tells you. It doesn't tell you increasing or decreasing. It tells you concavity. I know I'm concave up, then concave down, and then concave up. So if I want to know. Did you put that into the original? No, the second derivative. Because it's my second derivative sign chart. That one will tell you concavity. If I go to the first, or the original function, well, the original function will tell me y values on the function. The first derivative will tell me the slope of the original function. And the second derivative will tell you concavity for the original function. Any questions so far? They are both points of inflection, correct? So it says label the inflection points on the graph. I did find those points using the second derivative. Now, if I say the word point, what does that mean? I need to do a little bit of work because I need a y value. So I need to take those 2 points, and where do I plug them in to find a y value? The original. So again, recap. Original gives you y values. First derivative gives you slope. Second derivative gives you concavity. So negative radical 2, it works out nice. Both of those are going to give you the same value when I plug them in, right? Do I need a calculator for this? Yeah. No, I don't. Okay. Square root of 2 to the 4th is 4, right? This is just 2, right? So negative 20 plus 8 is negative 12. Any questions about that? That's how you find points of inflection. You will see me abbreviate these as POIs. Points of inflection. Turns out the second derivative, and I'm going to back up before I do that and look at this graph a little bit more. The second derivative can actually tell us a little more than just concavity and points of inflection. It can actually also tell us a little bit about maxes and mins, relative maxes and mins. We already have the first derivative test, and it's great, but it doesn't get us everything. Sometimes we can't find things with the first derivative test. You'll find that out later. The first derivative test tests for maxes and mins by changing increasing to decreasing. Do you remember that? Was that your question? Yeah. So the first derivative test, you find the first derivative, you set it equal to 0, and you look for changes in the sign of the first derivative. Does that make sense? We're going to look at what's called the second derivative test today, and it also tests for relative maxes and mins. What it does is it takes the critical points. You have to find those with the first derivative, which we know that. So if I knew this critical point, which I don't, but if I did, and I knew that this was concave up, if I had a critical point on a concave up graph, what kind of extrema would that be? Minimum. If I had a critical point on a concave down graph, I would have a maximum. And that is the second derivative test. If the first derivative equals 0, so we have a critical point, regular critical point. Remember, points of inflection aren't the same as critical points. So we have a first derivative equals 0, and the second derivative is negative, which means we would be concave down, then we have a local maximum at C. If the first derivative is 0 and the second derivative is positive, then we have a local minimum at C. The second derivative test fails if the second derivative equals 0 or doesn't exist at C. We would have to go back to the first derivative test. For most cases, the first derivative test is better. However, there are some cases you have to have the second derivative test. And if you've had any other AP classes, you know that AP is a master of finding ways to use strange things like that. So they will definitely make you use the second derivative test occasionally. A lot of times they'll show up on table sheets. Use the second derivative test to identify relative extrema on the function. It also comes in handy when you are without a calculator. Occasionally, the second derivative test is nicer. On polynomials, the second derivative is usually a little easier to deal with than the first derivative. So, no matter what, if I'm going to find extrema, what's the first thing I have to do? Find the first derivative, set it equal to 0. No matter what way that I'm identifying relative extrema, I have to find the critical points first. So I'm going to find the first derivative and set it equal to 0. Mental note, you might want to write this in your notes. Because they're taught on the same day, everyone teaches them on the same day. A lot of people get confused with the second derivative test and concavity. The second derivative test does not test for concavity. It uses concavity to see if a critical point's a maximum or a minimum. So for justification purposes, if you quote the second derivative test, you should be finding maxes and mins, not concavity. If you're finding concavity, you just say, because the second derivative is greater than 0, it's concave up. You don't have to quote any test or any theorem for that. So what everyone got? Now, if I were doing a first derivative test, I would put those on the sign chart, and I would use the increasing, decreasing behavior to tell which ones are maxes and mins. Second derivative test is different. I'm going to find the second derivative. And I'm going to find the second derivative at square root of 6, second derivative at 0, and the second derivative at negative square root of 6. quick mental note, would I have to plug 3 things in at the first derivative test as well? In fact, I'd have to plug in 4 things because I'd have to do something on the left and right of each piece, right? So I'm not doing any more work than a first derivative test. I'm doing the exact same thing I would normally have to do. So I plug in the square root of 6 into the second derivative. It's positive. That's all I need to know, right? In fact, I'm just going to write positive. And if I plug in 0, I get negative 24, negative. So the square root of 6 is what? If my second derivative is positive, it's okay to do your hands like this. I won't judge you if you're on a test making parabolas with your hands. The second derivative is positive, which means I'm concave up, which means I have a minimum. Concave down, which means I have a, and concave up, which means I have a. So relative min, relative max, relative min. Does everyone see how this gave you the same thing the first derivative test did, just in a different way? Almost identical workload. Now, if the derivative is difficult to calculate, the second derivative is difficult to calculate, you don't want to use the second derivative test. You only want to use it when you have to or on your homework when it tells you to. One of the two. Yes. This did ask me to find the relative extrema. Have I done that yet? Close. What do I need to do to actually find a y? I need a y value. So, but I did identify which one's maxes and mins. To find the y value, I have to go back to the original. The f of 0 is pretty easy. 8. Negative 28, go down again. What is it? X to the 4th, is that what it was?
36 plus 3.
Times 12x.
We have 36 minus 72.
And so we've got, this is 36, right? 72 times 12 times 6. So that's negative 36 plus 8, which is negative 28. So we have a relative minimum of negative 28 at both positive and negative values. Any questions about those? Even if those had been different for relative extrema, you could have 2 relative mins. That's okay. Mental note that. So that's essentially what we're learning today. Concavity and second derivative tests. So we're going to do some more examples, but that's the big information of today. We can tell if a function is concave up or down by looking at when the second derivative is positive or negative. And we can find relative extrema using the second derivative test. So, sketch a complete graph of the following function. And this is hoping that we do this without a calculator, I imagine. Before I go to sketch, I'm just going to find out everything, so kind of putting everything we know together. What can I find out without a calculator about this function? So I'm going to start with information from f of x. What could I have found out in Algebra 2? Before I entered calculus or trig or anything of that nature, what could I have found out about this function? Could I find the x-intercepts? What are they? 0. Good. And 2.5. Could I find the y-intercept? If you have an x-intercept of 0, the y-intercept has to be 0. That's not a point. End behavior. I could find end behavior by looking at, now this is a little bit calculus. I could look at the limit as x approaches infinity and the limit as x approaches negative infinity. My leading term there would be 2x to the 5/3 if you, yes, 5/3. Anyway, the leading term is positive. That would be the leading term, right? As x approaches infinity, what does that do? Goes to infinity, right? What about as x approaches negative infinity? Does everyone agree? Anyone have a question about that infinity or negative infinity thing? A fifth power and a cube root don't get rid of a negative, so negative would still be negative. If that were an even exponent, if the 5 were a 6 or something like that, then it would still be positive. So we could learn all of that from algebra 2. The derivative. There are 2 ways you could work this derivative. Someone give me the 2 ways. I can do product chain rule, or I could finish this thought that I have right here. I just distributed the x to the 2/3 to both pieces, added exponents.
Okay.
Why would I want to do that? I just do calculus. Probably easier to use your algebra skills to make your calculus easier. So 10/3 x to the 2/3 minus 10/3 x.
I was confused about the 5/3 because there's a 5 that pushes this is the 2 plus 3.
The 5/3 is because of the
That's the 3
1, which is a 3.
I saw the guys at the end.
I'm glad I did that then. Write that out. To simplify this, I'm going to need to rewrite and get a common denominator so that I can find when it equals 0 and go from there. This one's a pretty nasty one. This would be 10x to the 2/3 over 3 minus 10 over 3x to the 1/3 or cube root of x. Everyone agree with that? Essentially, what's the only change I made in that step? The x to the negative 1/3, put it on the bottom where it goes. To add these together, I do need a common denominator. What does the left-hand fraction need? Which, in a weird sort of way, turns out really nice. Why? Good. I just end up with 10x on this piece. 10x minus 10 over 3x to 1/3. So when does that equal 0? At 1. How'd you get that? Top has to equal 0. And when is it undefined? Okay. So this is my f prime sign chart. plug in something less than 0, like -1. I get a negative on top and a negative on bottom, which makes it positive. 0.5, I would get a negative on top, but a positive on the bottom. Does everyone know how I'm getting those? Good. And then after 1, positive. So my function is increasing from negative infinity to 0 and 1 to infinity, and it is decreasing from 0 to 1. Relative extrema, I have a relative max at 0, which that's the 0.00, would you agree? Because I found that earlier. That's what x is not intersect. And I have a relative min at 1, -3. Any questions so far? Second derivative information? No. I know some of you are thinking, man, this is a long question. Is this an AP question? No. You're seeing the full scope of everything you could find with this one function. So you probably won't ever see a question of this detail on an AP exam that asks you to do all of it. But we're just finding all of the different things we could find if we wanted to. Second derivative. Okay, the second derivative. This is where it really comes in handy that you've put your made this just a power rule problem, so that you just have to do power rule again. And so 2/3 times 10/3 is 29. X to the negative 1/3 plus 10/9 x to the negative 2/3. No, negative 4/3. Again, I picked a yucky one so you could see the fun time. Alright, so to find when this equals 0, I need to get a common denominator, so I need to rewrite it. So we need an x on the left, we need another x. Does everyone agree? Top and bottom. Bless you. So I get 20x plus 10 over 9x to the 4/3. Top equals 0 at negative 1/2. Label my sign chart as a second derivative and undefined at 0. The second derivative left of negative 1/2, so at negative 2, I would get a negative on the top. What do you notice about that denominator, though? It is at 0, but only at 0, though. What does that 4/3 power mean? To the 4th power. So the denominator will never be negative because I'm raising it to an even power. So I have a negative over a positive, which is a negative. Then I have, if I do negative 1/4, 20 times negative 1/4 is positive, right? So negative 5 plus 10, which is 5. Positive over a positive, which is positive. But then over here it would still be positive. So, quick question on points of inflection. Are they both points of inflection?
No.
Now, which one is the only point of inflection? So, I'll go find that y value in a moment. And then concavity. When is this function concave down? That's all. And then it's concave up. Good. 2 options for this. You can do negative 1/2 to 0 and 0 to infinity. The AP exam would also accept negative 1/2 to infinity. They would accept either answer on that concavity. So both of those are great. Points of inflection at negative 1/2. And my original. That's not a pretty number, is it? Or cube root of 1/4. We'll do a calculator on this one. Only one. Right back. There is not today. Got Tuesday, Wednesday, and Thursday. Speaking of, I'm still missing calculations 10 and 28. So if you would look for those. I need the denominators to be the same, and this is an x to the 4/3. So I needed the 1/3 to become a 4/3. When you multiply, you add. Okay, and did someone get that point?
47.
All right. Now here's the cool part. Not that this is something that we're going to do all the time. In fact, rarely, if ever. But we can graph this entire thing really, really well without picking up a calculator. Even if we hadn't known that y value, it wouldn't have been necessary to graph to know the y value of the point of inflection. So let's put down on a graph everything we know. Oh, sorry. Thank you. Good call. Okay, so 0, 0 was, so I'm walking through the top information. 0, 0 was an x and y intercept. What was the other x intercept? 2.5. And then I had a relative my in behavior is this. We'll mental note that. I had a relative extrema, a maximum at, what was my maximum? 0, 0. Okay, so this does this at some level. And then what about my relative minimum? 1, negative 3. Okay. And then I am increasing, then decreasing, and then increasing. Is that correct? What it looks like. And then my concavity is I am concave down until -1/2. And then I changed to concave up. That's not what my picture looks like. 0 was a maximum. Is that right? No. We will use it. Okay, so -1/2 and negative. What was that? -3.7. Let's check that second derivative.
Is it? I thought it would be like that.
Time out.
Oh no.
Hold on. No, that's right. 29. So negative 10 9. Good. Hey. What's fun? Oh, we have one. So we should. Okay, graph it real quick. What did we do wrong? We'll finish this one tomorrow.
I told you.
Good question. Okay.
Why would you ask?
Stop talking. We'll finish this. I'll have to look at that video one time. Okay. Really quick. Talk about your homework. Hey, this page right here and that packet are both due on Thursday. So you got quite a bit of time. We're going to finish the notes. Now, you didn't learn break testing. You haven't learned everything. You've learned all of the Extrema. You just haven't seen all the examples. So you can probably do all of this homework now. The bookwork is a little easier than the packet. If you want to start there, it just says basic, find the concavity, find the information. So it's a little easier if you want to start there. We'll finish the notes tomorrow. Wednesday we will have a work day. Thursday we will even have more kind of process time because we're going to play a matching game. So, got a lot of stuff to work on this one. I like it. That's the time.
was under 7. I thought it was 7.
I think it was 4.
It's 4? What is it? I feel like drafted. It looked like 6, but 6 wasn't enough.
Maybe you can do conversion. Alright. Well, you want to turn it early, would you?
Combo?
Well, 32.